Hey everyone, this is 12.2 Fundamental Counting Principle. We've used this principle already in the last section every time we do what I call the slot method. So it says if you want to perform a series of tasks, those are like your slots, and the first task can be done in A ways, second can be done in B ways, third can be done in C, and so on, then all the tasks can be done in A times B times C times etc. ways. So basically it's just saying that if you line up your slots, you plug in the number of ways you can do each task. If you multiply all those numbers together, that'll give you the total number of ways you can combine them all together. So we'll see some examples here of how you might use that. Alright, on page 620, number 5, we're building a home theater system. It says Elaine's building a system consisting of a tuner, an optical disc player, speakers, and a high-definition TV. And then we have numbers for each of these. So let's just go ahead and start with the slots. We have a tuner first. Oops, it's a little big. So we've got a tuner. Then we have speakers, optical disc players, so I'll just do CD, and 5 TVs. How many ways can she configure her system? So those are our slots: tuners, speakers, TVs, and disc players. And we're going to plug in the number of options we have for each. It says 4 tuners, 8 speakers, 3 disc players, and 5 TVs. And then the fundamental counting principle says, since we plugged in all the different ways you can do each thing, if we multiply this together, we'll get the total number of options or total number of combinations. So that amounts to 480 home theater systems. So this is pretty standard application of the fundamental counting principle. It's a lot like the kind of classic example I often use is making an outfit. If you have 4 jackets, 8 ties, 3 shirts, and 5 pants or something like that, you'd have pretty much the same setup. Alright, on page 620, we have some numbers here that they want us to create 4-digit numbers using the digits 0 through 9. The first thing that I want to note about that is that if you have the digits 0 through 9, that's actually 10 digits. So a lot of people make the mistake of listing 9 options when you actually have 10 because you're including 0. So for all these problems, we want to make 4-digit numbers using those 10 digits from 0 to 9. And on number 14 it says the number must begin and end with an odd digit. Digits may not be repeated. So we have these two kind of conditions that we have to satisfy when we make our number. So let's go ahead and line up 4 slots for our 4 digits, right? So it's a 4-digit number, and what we're going to enter in the slots are the number of digits we can choose for each slot. So the first thing says it must begin and end in an odd digit, and digits may not be repeated. So if it has to begin with an odd digit, from 0 to 9, there should be 5 odd digits. Right? Those are the numbers 1, 3, 5, 7, and 9. Now, it also has to end in an odd digit, so there's 5 odd digits, but since digits may not be repeated, basically we're saying that in this first slot you can choose any of the 5 odds, but once you choose one, you only have 4 of the odd numbers left to use. So we're actually going to enter 4 here. So again, when you start this, by the way, I usually recommend starting in the most restrictive places, so that's why we're starting with the odds here. We're assuming we haven't picked any numbers for the very first slot, and you can choose any of the 5 odds, but once you choose one of those numbers, you can only choose from 4 other odd numbers that are left. That's because digits may not be repeated. So keep in mind what you're looking for, that there's odd digits in this case, and when there's no repetition allowed, you have to count down essentially as you keep using those types of numbers. So now the middle slots, we don't have any restrictions on these other than the fact that digits may not be repeated. So notice, since we filled in the first and last slot, we've already used 2 of the odd digits. So out of all the 10 digits, we've used 2 already. That means there are 8 choices here. That would be any of the evens plus the 3 odds that you haven't used yet. And then once you pick a slot there, you've already used 1, 2, 3 numbers, right, out of the 10 numbers that you can choose. So there's only 7 left you can choose from. There we go. Now, first thing to notice is that this is not the number 5,874. Right? We're not actually building a 4-digit number. We're coming up with the number of 4-digit numbers that we can build using those digits, using first and last odd, and not repeating. So these are the number, each of these numbers, 5, 8, 7, and 4, represent the number of choices we have for each slot. So if we want to figure out the total number of choices altogether, we're going to multiply. So if you multiply these 4 numbers together using that fundamental counting principle, you get 1,120 4-digit numbers. And that's your answer here, right? So pretty kind of a standard example of fundamental counting principle where they're giving you restrictions on the slots. I usually recommend, like I said, starting with the most restrictive slots, in this case, that first and last odd digit. Alright, same type of problem. We're still using the digits 0 through 9, so that's 10 digits. This time it says the number must be odd and greater than 5,000, and digits may be repeated. So let's line up our 4 slots. The number must be odd and greater than 5,000. Well, if the number must be odd, that means we're going to be dealing with the last slot, right? That last slot can be any of the 1, 3, 5, 7, or 9, which is the 5 odd numbers. Okay. So that last slot there, the 5, stands for the number of odds we can choose. Because remember, a number in general is odd as long as the last digit is odd. So that takes care of the odd part. Greater than 5,000 means our first slot over here, the thousands place, needs to be 5 or bigger, right? So if you're looking at the digits 0 through 9, you have the numbers 5, 6, 7, 8, and 9. That's 5 values you can choose. Oops. 5 values you can choose that are 5 or bigger, right? 5, 6, 7, 8, and 9. Because we have to have those numbers in the thousands spot to guarantee that our number is greater than 5,000. So notice also it says digits may be repeated. That's why I'm not counting down in this case. This 5 at the end over here, this 5, represents the number of odd digits I can choose from to make it odd. And the number in this slot represents the number of values that are greater than 5 so that I can make this number greater than 5,000. 5, 6, 7, 8, and 9. Alright, and then the numbers in the middle, we don't have any restrictions. We've already satisfied this first condition. It says digits may be repeated, so I actually can use any of the digits in each slot. Remember, there's 10 for each, 10 options for each, 0 through 9 and 0 through 9. So those numbers 10 represent the number of numbers I can choose for each slot. So there we go. We have filled in our slots, multiplied all together. In this case, you'll get 75,000. 2,500. We'll get 2,500 here. Oops. And these are 4-digit numbers again. Right, so again, 2,500 represents the number of 4-digit numbers we can create. Notice we're not actually listing the numbers because there would be a big list for one. So keep in mind this is the number of 4-digit numbers we can create with these conditions. Okay, on page 620, we're going to take a look at number 17. And it says, in how many ways can you choose answers to an 8-question true or false quiz? All right, so we have this, this true or false quiz with 8 questions. Each question has 2 options, right? True or false. So let's set up slots. 1, 2, 3, 4, 5, 6, 7, 8. Right? So 8 questions representing, 8 slots representing the 8 questions. And each question you can choose true or false, which means it has 2 options for each slot. And then if you multiply this all together, that's 2 to the 8th, which happens to be 256. 2 times 2 times 2 times 2, etc. And this is 256 ways to answer. So that's all the possible outcomes. Obviously, a common kind of tricky question is how many ways are there to answer the question and get them all correct? Well, that would be 1, right? Because there's one combination of trues and falses that is actually the correct answers to each problem. This is just all the possible ways. So there's the one right way, plus all the 255 different ways you can get the wrong answers. So that's what we just figured out in that problem. On page 621, this time we're counting license plates. It says in a certain state, license plates consist of 2 letters followed by 3 digits. How many such license plates are possible? Well, they're given us slots, right? 2 letters. Here's our letter slots, followed by 1, 2, 3 digits. So the letters in the alphabet, there are 26 of them. I'm just double checking. It doesn't say anything about repetition, so we're assuming repetition is okay. So you can choose any of the two. You can choose any of the 26 letters for the first 2 slots, and then for digits, we're assuming the digits 0 through 9 again. So any of the 10 values from 0 through 9 for the last 3 slots. Multiply this all together and get ready. It's a big one. 676,000. Different license plates you can create if you have 2 letters followed by 3 digits. Now it says if the State Department decides to change the plates to have 3 letters followed by 2 digits, so we're going to flip it. 1, 2, 3 letters, 2 digits. This time you have 26, 26, 26. You can probably guess already it's going to be quite a bit bigger. In this case you'll get 1,575,600 different license plates you can create using those restrictions. Alright, this last problem is a little bit more challenging one, kind of like actually all these with slots. It's on page 618, example 6, and it's talking about how you can sit students in a row, basically, with some extra conditions. So let's check this one out. It says, this professor teaches some psychology class of 10 students, so there's 10 students total. She has a visually challenged student, Louise, who must sit in the front row next to her tutor, who is also a member of the class. So we have Louise and the tutor. They are 2 of the 10 students, and Louise and the tutor have to sit next to each other. It says if there are 6 chairs in the first row of the classroom, how many different ways can we assign students to sit in the first row? So we have 6 chairs in the first row. We're going to start out with 6 slots, which I've kind of drawn for you over here. And because we have to have Louise and her tutor next to each other, let's just start by assuming Louise can sit here and the tutor can sit there. Right, so the front left corner. That would leave that they are 2 of the 10 students, so that would leave 8 students to choose for this slot, 7 for this one, 6 for this one, and 5 for that one. Right, so assuming we put Louise and the tutor in the first slot, there are 8 times 7 times 6 times 5 different ways we can fill the rest of the slots. This number, by the way, is 1680. That's the 8 times 7 times 6 times 5. But that's if we put them in the first slot. Let's say that we shift them over a second and we put them next to each other, but in the next 2 slots, then we could choose 8 students here, 7 here, 6 here, 5 here. We'll notice again that gives 1680 ways if they're in the second 2 slots. And you can kind of do this by shifting them over each time, right? And each of these are going to give the 1680. So it's going to be this number 1680 times 5. Why 5? Because that's how many times we could shift them over. They're 1, 2, 3, 4, 5. So for the 5 positions we can put them in, there are 1680 ways to fill the rest of the seats for each of those. So if you take that 1680 and multiply by 5, that'll give you the number of ways you can arrange this. Now, we're missing one detail though. We put Louise on the left of the tutor. Well, what if we flip them? Well, you can probably picture that. Put the tutor here and Louise there, then you have 8, 7, 6, 5 ways to fill the rest of the slots, right? Well, same thing. We can shift the tutor and Louise. This is still 1680, and we can still shift them down 5 different ways. So notice what we've just figured out, though, is we need an extra factor of 2. It's this 1680 times 5 up here. 1680 times 5 ways to do it if Louise is on the left, 1680 times 5 ways to do it if Louise is on the right. So we're just going to take this number, 1680 times 5, and multiply it by 2. Right, so our actual answer here, if we want to calculate the total number of ways we can do this, it'll be those 3 numbers, 1680, the way we can fill the other 4 seats, times 5, the number of ways we can shift Louise and her tutor, times 2 the number of ways we can flip Luis and the tutor. And this will just give us 16,800 seating arrangements. We'll just call it seating plans. Alright, so that's a more challenging example where you have some conditions you have to deal with and you're not really sure exactly how many options it's going to give you for each kind of thing. So just throw out the 6 slots and start shuffling things around, and you'll start to see these patterns. No matter where you put Luis in the tutor, there's still 8 times 7 times 6 times 5 ways to fill it. You can shift Luis in the tutor 5 ways, and you can flip their order 2 ways. Right? So I think there's a similar problem on the homework where it says Luis has to be on the left of the tutor. Well, then in that case, you wouldn't have that times 2, right? Because you can't flip them over. So stuff like that. So I hope this helps. Let me know if you have any questions, and keep up all the good work.